So let's finish. I think this proof of the hardness of uniform reliability. Now that we've started it, so to recap the context a little bit, I want to show that uniform reliability for this this query. For this query here, RST for this RST query is sharply hard. And for this, I want to reduce from counting the independent sets of the bipartite graph. And actually, as an intermediate step, what I really want to reduce from is for counting for all ijk, the number of vertex subsets having I, j, and k edges of each type. So with no incident vertex, one incident vertex, and two incident vertices. And I want to do this using an oracle for uniform reliability for that query. And I want to invoke the oracle on an instance that looks a bit like the bipartite graph on which I want to do the counting. But I don't just want to invoke it on one single instance, because this is going to give me one value. And I would want to get as many values as I have ijk, so a cubic number of values. To do this, instead of doing just the oracle on this single instance, I do it on a cubic number of instances, and I define the instances by replacing the S edges by a back and forth path like this, that also gives me matches of the query, possible matches of the query. And how many of these paths I put per edge is the value P. So I will do one reduction where each edge is replaced by one path, one reduction where each edge is replaced by two parallel paths, one reduction where it's three parallel paths, and so on. Okay, these are the oracle calls that I will do, and let's see that the values given to me by the oracle, the number of sub-instances of these that satisfy the query, is giving me information about what I wanted to know on the original bipartite graph. So it sounds like the connection between the two is pretty distant, but in fact, I think the connection is not that complicated to see after all. So what is the oracle telling us? So we are coding the oracle on something like this, which is the coding of the initial bipartite graph by replacing each edge with parallel paths like this. Here, there are like two parallel paths. The oracle tells us how many subinstances will actually satisfy the query, so contain three facts RST like this adjacent to each other. But up to doing the complement, again, it's telling me how many subinstances violate the query. So how many, the oracle is a magic box that tells me, given this complicated thing here, how many subinstances do not contain any triple RST like that, okay? So I want to relate the answers of the oracle. So how many subinstances of this thing for p equals 2 do not have any RST? And the oracle is also giving me the answer for one parallel path, for three parallel paths, and so on. And I have these values and one that are the oracle answers. How can I relate these values to the subset, the number of edge subsets of the bipartite graph that I wanted to count? And here is the connection. When you choose a possible world of this graph, so a subset of facts of this graph, we can first see what you choose about these extreme left R facts and these extreme right T facts. You need to choose whether to keep or discard them. And this corresponds basically to a choice of edge subset, of vertex subset, sorry, of the initial bipartite graph. So there's a bijection between these two things of the subsets of edges to the left and the subset of vertices to the left and the subsets of kept facts to the left and right on this instance. Okay, there's a bijection between the two. And now, what is the answer of the oracle on this instance? Well, we can say the answer of the oracle on this instance is the sum of the possible worlds that do not contain RST for each choice of kept facts in the pink boxes. So I sum over the choices for the pink boxes, and now I have the number of possibilities of subinstances, having fixed the left and the right facts. Okay. And now, why do I fix the left and right facts? It's because now all of the gadgets, they are independent from one another. You see, knowing whether I have or not this pattern here, I can determine it by looking separately at the gadget here, the gadget here, because the endpoints have been fixed, and so there is no longer any correlation between these gadgets. So if I take one copy of the gadget, so this is one copy of the gadget for p equals 2, I have 4 possibilities. Either this was kept and this one discarded, or the other way around, this one was discarded, this one was kept, or both were kept or both were discarded. And so I have 4 types of gadgets, and all gadgets of one type, they are actually the same, right? They behave the same way. So if I say, for instance, I keep this one and I discard that one, the probability of having this, the number of subinstances containing this, is the same, no matter where the gadget is located. So in the end, all that matters is how many gadgets I have of type 0, 0, of type 0, 1, of type 1, 0, and of type 1, 1. And this is precisely the quantities on the number of gadgets of this type is precisely the number of edges with 2 kept facts like this. And the number of gadgets of this type is precisely the number of edges that are like this and like this. Okay. So this means that how many possible worlds of the complicated TID that looked like this? I have, for a given choice of R prime and T prime, which is telling me what I keep and what I discard, is how many gadgets of, is something describing the behavior of this gadget to the power, how many edges do I have in the bipartite graph where there are no kept vertices. This is the some behavior of this gadget or that gadget. They are the same, they're symmetric, times how many edges of the bipartite graph are of this kind. So if, for instance, so like, let's say I have taken it like this, so now I have this I find here. And how many edges of the bipart, so the behavior of the gadget where I kept the 2 extreme facts, times how many I have of this in the bipartite graph. So these are these 2 edges here and here. So I'm not sure that this is so clear. So like to try and explain again, you see that I'm considering all subsets of vertices of the bipartite graph to the left. Each of subset like this corresponds to a choice of the pink facts in the instance to the left and right. And when I have fixed the pink facts, the probability of the query can be determined by looking at each gadget separately, seeing its type, so whether its endpoint vertices were kept or not, and how many gadgets of each type I have is how many edges of each type I have in the initial bipartite graph. So this is where there's a connection between the 2. So now you see, so I mean, so the next step I'm going to skip it because it's scary and it's not especially interesting. The next step is computing these exact values of how many possible worlds I have in a gadget where I decided to keep the left and to discard the right or stuff like that. This depends, of course, on the number P of how many parallel copies I have. In fact, it means I can just look at this and exponentiate to P to know the total number of possibilities. So I get that NPBB, so the number of possible worlds when I have P parallel copies and type BB prime, it's just NBB prime to P, where NBB prime is the type where I have just one parallel copy. And I can explicitly compute these values. I get these very nice numbers. And it's not because I like explicit computation, but it's important that these numbers contain prime factors that are distinct. Because when you put everything together, the answer of the oracle on a coding where P has some value is obtained by summing over the pink choices to the left and right and looking at how many possibilities I have, having made the choices indicated by in these pink boxes. And this is some quantity to the power P, because I have this exponent P everywhere. And it's the number of possible worlds in each gadget type. So now there are no parallel paths. They're just like, they just look like this, the possible gadget types, to the power of how many edges of each type did I have. And this means that since the R primes and T primes of the same type cardinalities, so the same C00, C01, C11 behave the same way, I can instead decide to sum over the possible cardinalities of types. And I have as many terms in my sum as I have subsets of vertices of the bipartite graph having these type cardinalities. And this allows me to make this quantity appear, so the number of subsets of vertices of the bipartite graph having these cardinalities. This is the quantity that I'm supposed to compute to perform the reduction. And now you see that it's connected to the oracle result. So we've managed to connect on our bipartite graph. We are counting vertex subsets. This is what we want to do to complete the reduction. We are coding this as a complicated instance, but where we have choices to make on some specific facts. And the parameterization by these cardinalities allows me to relate. It allows me to know how many possible worlds here do I have depending on these cardinalities. And so it allows me to make the right X, it allows me to make the X quantities appear. And this is in fact a linear equation system. So you see to the left, you have the possible oracle results on the codings for 1 parallel paths, 2 parallel paths, 3 parallel paths of the same bipartite graph. And they are related to the number of vertex subsets of the bipartite graph having these cardinalities of edge types by a mysterious matrix whose coefficients are n00i, n10j, n11k to the p. So the power p corresponds to the number of parallel paths in the coding. The ijk correspond to the, and the ijk correspond to the row. So the p is the P corresponds to the, no, sorry, P corresponds to the row, ijk corresponds to the column, and n00, n10, and n11 are just explicit constants, like fixed constants that we can compute explicitly if we want. And I'm not going to show that this, and basically now I can conclude the proof by showing that this equation system is invertible, that this matrix here is an invertible matrix. And the key point for this is that this is a van der Monde matrix. I mean, it's a matrix of quantities, like different quantities here. So these are just some values put to different powers. And so we need to show that these values are never, I cannot get the same value here with different ijk. And this uses the prime number decomposition from before to argue for that they cannot get the same number by different ijks. So different type cardinalities. So I'm skipping a bit the details because I have a feeling that I've lost some people, but this is the high level idea of the unweighted reliability proof. So I propose to continue. So we've covered with this, so I'm skipping the invertibility part. So relative to what I intended to do in the talk, so we have covered self-join free CQs, upper and lower bound. I propose to skip the case of UCQs, which would have been the next step, and to jump directly to the case of unbounded UCQs. So these are like the more complicated queries with because this is the recent result of mine from ICDT 20. To say a word about the UCQ case that I'm skipping over. So UCQs, basically, so we can use the same relation symbol in multiple places, and we can have unions, so disjunctions across two things, and it makes the picture much more complicated. So the upper bound is by an algorithm that resembles a bit the self-join free CQ algorithm, but it's much more complicated. And in particular, it does inclusion-exclusion computations. So we can no longer represent what it does in terms of a provenance circuit. And we don't, it's an open question whether we actually can do it. And the lower bound is shown in the article by Dalby and Suchu, and it's an extremely complicated result that whenever this complicated algorithm fails and doesn't manage to compute the probability of a query, then you can actually show Sharpe hardness of that query. But this is something that wasn't reasonable to present in any case. So, I mean, this is the story for UCQs, even though I won't cover it in more details. And now let's jump to more expressive queries for recent results. Okay, so in the rest of the talk, so we have, how much time do we have? So we have like 35 minutes. I hope to be able to cover maybe not all of that proof, but at least a good part of it. So this is a different, in terms of techniques, this is a different hardness proof. And the techniques are pretty different. So the proof I presented for uniform reliability, it might look a bit unpalatable to you because of all of these matrices and countings and stuff, but it's a fairly standard technique that's used in several places in this area and in all other counting problems. The proof here doesn't use any of that stuff, and it's based instead on query homomorphisms. So it's more, I mean, it's a more structural proof, let's say. So just to, you're not going to hear something that looks like the previous proof. If you didn't like the previous proof, hopefully maybe you will like this one better. And I have the suspicion that what goes on in that proof in terms of homomorphisms, at least part of it, like should be useful for other things. Like it looked like natural concepts, but I haven't been able to connect them to anything else. So if you see, if this reminds you of something, I'm interested. So this is only about probabilistic reevaluation, so no uniform reliability. And it applies to queries beyond unions of conjunctive queries and even beyond first order. And I actually don't care so what's strange about that proof is that this is a proof about the query language that's not really specified. I don't know how to actually write down a query in that language. I just use a semantic property of the query, which is that they are closed on the homomorphisms. So this is a very standalone definition and unrelated to anything else. If I have a query, so a query is something that takes an instance and says either yes or no. I have a query. If an instance satisfies the query and the instance has a homomorphisms to another instance like this, then the other instance must also satisfy the query. So again, Q is closed on the homomorphisms means if I satisfies Q and I has a homomorphism to I prime, then I prime also satisfies Q. And so in particular, this is true for conjunctive queries or unions of conjunctive queries, right? If Q is a union of is a conjunctive query, let's say Q is a CQ. If I satisfies the CQQ, it means Q has a homomorphism to I. And so if I also has a homomorphism to I prime, then by composition, I know Q also has a homomorphism to I prime, and so I prime also satisfies Q. Okay. So this is a property that's satisfied by conjunctive queries and unions of conjunctive queries. And we're just taking an arbitrary query that has this property. So for instance, like another kind of query that has this property is what's called the regular path query. So a regular path query is a query of the form a regular expression like this, and it's just saying, I have a path in my instance that forms a word in the language of that regular expression. So this is a query, which is not a union of conjunctive queries because there are infinitely many different path lengths, but it is closed under homomorphisms, right? Because if I have a match of something like this in an instance, and I have a homomorphism from this instance to another instance, and again, I have a match of that path. So and this is just to argue that these queries closed under homomorphisms, they contain all UCQs and they contain also very different things. Another way to think about queries closed under homomorphisms is to think of them as infinite unions of conjunctive queries. So I write this, so I write queries closed under homomorphisms UCQ infinity like this, because it's like if I had a disjunction over CQs, but I have infinitely many CQs. So for instance, this RS star T query, it's just a disjunction over all of these conjunctive queries. This, or this, or this, and I have infinitely many disjuncts. So I can't generally write an infinite union of conjunctive queries can be very strange, right? It could be like the disjuncts have very unpredictable properties, and since it's an infinite set, I cannot explicitly write it. But I don't care. I'm just saying I have a query closed in the homomorphisms. I don't want to write down explicitly the list of what the query is. It's just I have this query. Okay, it's a function from instances to true or false that is closed in the homomorphism. And I want to show that, in fact, all of these queries are intractable for probabilistic query evaluation, no matter how weirdly they've been defined. Any query that's like this is intractable, except if it's actually equivalent to a UCQ, which is known to be tractable. So because there were some tractable queries closed on the homomorphisms, we've seen like the hierarchical queries before, and so more generally tractable unions of conjunctive queries. So a query closed on the homomorphisms is an infinite union of CQs. If I can write it actually as a finite union of CQs, so as a UCQ, then I say it's a bounded UCQ infinity, a bounded query closed on the homomorphisms. And conversely, an unbounded query closed on the homomorphisms is a query that's an infinite union of CQs, but cannot be written as a finite union of CQs. So it's not expressible as a UCQ. For instance, so this RS star T query, if I write it as an infinite union of CQs, it cannot be written as a finite union of CQs. And so it's not local, so it's not first order. Okay. So my claim is about those queries closed on the homomorphisms that are not equivalent to UCQs. So basically any query closed on the homomorphism that does some kind of reachability computation, or like lots of things that cannot be just expressed as a finite list of patterns that I want to find, then probabilistic query evaluation is always sharply hard. There is just this technical restriction that I can only do this on an RET2 signature for now. I don't know how to show it for arbitrary RET databases. I'm actively working on trying to lift this restriction, and I hope to be able to do it. But the good news is that RET2 is much more pleasant to draw than arbitrary RET. So at least I think it's good news for what I'm explaining now, that I'm only going to be drawing stuff in RET2 and not in higher RET. I don't know either what happens for uniform reliability. I'm thinking about it, but I'm not sure it can be made to work. Okay. So to show this theorem, the proof is, I'm going to explain the proof, and it works in 2 steps. We're first going to look at very simple instances. And then we're going to generalize to arbitrary graphs. So these very simple instances, they look like this. They are basically bipartite graphs with RST facts. And these are things we've been seeing a lot this afternoon, right? So a bipartite RST instance, it has a left domain and a right domain. And it has edges between the two. So the edges, they are like S facts intuitively. So I have edges between the left and right. And I have some left vertices having an R fact and some right vertices having a T fact. So I can also have an S fact, not, okay, maybe I'm not being very clear here. So the domain of a bipartite RST instance, it has some elements, some domain elements called A's and some domain elements called B's. On some A's, I have the fact R. On other A's, I do not. On some B's, I have the fact T. And on some other B's, I do not. And I have some S facts like this. So this is both a restricted signature. So I have R, S, and T, like for the hard query. And it is an assumption of how the facts are used. So the R facts and T facts are disjoint, and S facts can only connect left and right elements. So it's like a kind of partitioned instance. And I can put probabilities on these instances by saying that the R facts are probabilistic and the S facts are probabilistic and the T facts are probabilistic. I'm going to use this as the hard problem for my reduction. So what I'm going to use as a hard problem is probabilistic query evaluation on these kind of instances for some specific queries. So let's see what the queries are. The first query is a query that you know very well. It's the RST query. So we know that this is sharply hard, right? We've seen that this query is hard, and in the reduction for that query, we were using only instances of that bipartite form. So this we've already seen. The second query is the same, but I'm using back and forth paths. So this is a bit reminiscent of the other proof. So this query is drawn like this. It's R, I have an S, I'm going back on an S, and then I'm going forward on an S. So it's R and T connected by back and forth path of S edges of length 3. And I do this for all possible lengths. And I claim that all of these queries are sharply hard on bipartite instances. And this is just because when I have when you take the hardness proof, so when you had, remember, x1, x2, y1, y2, and you had a pp2 DNF formula, we've seen how to code it by saying I have these facts R, T, and these S facts. Like this was the usual coding. But then if I want to make this coding work for Q2, I can simply do the same thing. And instead of one S edge, I do a back and forth path like this. And all of these edges have probability 1, like in the other reduction. So I hope it's clear that if you understood that part of that reduction of like from counting, so this is counting satisfying assignments of this PP2 DNF formula to counting possible worlds here that satisfy the query. It's the same as counting the possible worlds here that satisfy the query Q2. And I can do, if I take longer paths, I can do the same for any length QN. So all of these queries are hard. And so I can reduce from any of these queries on bipartite RST instances. And yeah, these instances that we build here, they are actually bipartite, right? Because the artifacts always go, these are left elements. These are left elements, these are right elements, these are left elements, and these are right elements. So it is actually a bipartite instance. And so these are the things from which I will reduce. So probabilistic reevaluation for the queries Q1 or Q2 or Qn. And I will also need another query, which is an unbounded query. I will also need the query that's the infinite disjunction of these queries. So this is just this RPQ. So this is a query on bipartite RST instances that asks, is there an R fact and a T fact that are connected by a back and forth S path of an arbitrary length? I don't care what the length is. And I claim that this is also a hard query. So it's not covered by anything done before because it's an unbounded query. And what's surprising is that I cannot apparently do the same reduction, because you see that if I wanted to do the same trick here, I cannot put an infinite path of S here. I can only choose one length. And then the problem is that I will always have paths connecting R's and T's that are not next to each other by going on one path and then back on another path and then forward on another path again. Or doing like this kind of back and forth in the graph. So if I take, for instance, these two variables in PP2 DNF, I take these two variables to be true, then the PP2 DNF formula is not satisfied. But in codings like this, I will always have a path going here and then back and then forward if I don't limit the length of the path. So this kind of coding actually does not work. Instead, we do a different coding, because it's fortunately the case that reachability in probabilistic graphs is known to be sharply hard. So if I have a graph and I want to know, like each edge has probability 1/2, and I distinguish two vertices S and T, and I want to know what's the probability that there's a path connecting S and T in a probabilistic graph like this, this is also a sharply hard problem. And now I can reduce from that problem to that problem by just doing a kind of instance that codes a graph like this, so that this will be the R fact, this will be the T fact, and these will be back and forth paths of S's. And if there's a path from S to T, it will mean that I have a back and forth path in my bipartite instance. I'm going to skip the details of how this coding is done, because I think it's reasonably intuitive that something like this can be done. So the end thing is that on these instances with R's and T's and S facts going back and forth like this, the queries, basically all of the reasonable queries are hard. So testing RST is hard, testing RSSST is hard, and so on. And even testing for the existence of a path of an arbitrary length is hard. All of these queries are hard. Is this reasonably clear? So these are the problems from which I will reduce. And so I'm saying on these restricted instance shapes, these queries here are sharply hard to compute. This one we had seen before. This one is a variant of that proof. And this one is possible by a different proof reducing from some different problem, like the reducing from reachability in probabilistic graphs. Okay. So the idea now is going to be, and now it's challenging to prove. So we have some UCQ, some infinite UCQ, some query close in the homomorphisms, and we want to show that probabilistic reevaluation for that query is sharply hard. And we don't know anything about that query except that it's unbounded. So how are we going to do a reduction? Because we don't know what the query is, so we really don't know its behavior. So we're going to get to know the query and like learn how the query behaves by like choosing instances on which the query is true and trying to isolate what exactly makes the query true in these instances. So this is like the general proof strategy, which I think is like it's original because of this like unusual case of showing hardness for a query that we don't even have a formalism in which we can write it. Okay. And the way we do things is if we find an instance, say we have an instance, in instances, we're going to be interested in the following pattern of facts. So we're going to be interested in the cases where we have 3 facts of the instances that are like this. So if I have an instance satisfying, so it will be interesting for instances satisfying the query, and it has 3 facts like this, I'm going to be interested in knowing whether the connectedness of these 3 facts is important to the query or whether it's not important. But before I do this, let me state that if I have an instance and 3 facts like this, I can code a bipartite instance into an instance with this choice of 3 facts by basically copying these facts in some way. So this is how we do it. This is, sorry, this is a bipartite instance. It's the thing from which, so we know that many queries are hard on this kind of instances. And so we like, on such instances, the behavior of queries cannot be that complicated intuitively. Now we have some random instance for a query that we don't understand anything about, but in the instance we have so the instance contains lots of facts and lots of arrows, and it's very complicated. But we have isolated 3 specific facts like this. If we want to code this bipartite instance into this, we're going to make copies of B and copies of C, and we're going to connect things together in the way that's prescribed by the bipartite instance. So let's see what it looks like. So you see, so this is some bipartite instance I prime. This is a graph instance I with a choice of 3 facts like this. And this is the coding of I prime in I. I don't know what's the way I've written it, coding of I prime in I. So let's take a moment to understand what this coding looks like. You see that B has been copied to 2 places and C has been copied to 2 places. Why is this? It's because my bipartite graph, there are 2 vertices to the left and two vertices to the right. The green fact has been copied according to the edges of the bipartite graph. And on the place where there is no edge, I still have this dashed green thing here. So this is a bit subtle. It's because this is because in my instance here, I have chosen one specific fact S of BC to do the coding, but there could be other facts on BC. So like on BC, there can be many facts in general, and I have chosen just one fact because I'm going to give a probability to only one fact, and I cannot give a probability to several facts at the same time. And I cannot give a probability to a bunch of facts and make them appear or disappear together. So I have chosen one fact, like which I met here. The green arrow actually means all the facts are here, including the chosen fact. The dashed green arrow means all the facts are here except the chosen fact. And as for the blue arrow is here for the left vertices for which there was an R-fact in the bipartite graph. So this guy here corresponds to this guy had an R-fact. So here we have the blue arrow. This guy did not have an R-fact, so we have again a dashed blue arrow, meaning we have all the facts between A and B except the facts that we chose. So this was the fact, well, so sorry, I messed up the names. This one is not S, but it's called V instead. And here I have chosen again some witnessing fact U of AB. And there could be other facts between these two elements. And I copy these in the dashed arrow, and in the full arrow, I also have the chosen fact U. And for the red arrows to the right, it's the same thing as to the left, except with the T facts and the red elements in the bipartite graph. And in my instance, I have chosen the facts on A, B, C, D, and I could have lots of different other facts involving B and A and D and whatever. These are just copy them so that like the copies of B, B1 and B2, they behave in the same way, like all of the facts involving B that are not the green, the three chosen facts, blue, green, and red. I just copy them so that they use the two copies B1 and B2 in the same fashion. And for this, the same way, I copy C1 and C2 and I do the same thing. So I mean, I don't know if you need to understand the process of that coding, but the idea is that, yeah, when I have a graph, I can code a bipartite instance in that graph by choosing three consecutive edges in my graph, copying the middle elements, and connecting things according to the bipartite graph. And the key point in that is that this preserves homomorphisms in the sense that if I have a bipartite graph here having a homomorphism to another bipartite graph, one can check that the coding here will have a homomorphism to the coding of this other bipartite graph. Because it's always like if you merge together elements of the bipartite graph, you can merge together elements of the coding and it will work in the same fashion. So the point of doing this is that I can think of the behavior of the query, like looking at the behavior of the query on the possible codings. I can talk about the behavior of a query on the bipartite graphs instead. And so this way I can leverage the hardness on the bipartite graphs to get hardness of the query on the graphs for this specific shape of graphs. In fact, I only need to use graphs of this specific shape to see that there is hardness. And it turns out that, so I have my query of which I want to show the hardness. So now we're going to have to choose an instance on which to do this kind of codings and on which to show hardness. So we fix some instance, so this is the instance, and some pattern, here is the pattern. And I can use a pattern to show hardness of the query on graph instances if the initial instance satisfies the query. So I mean, I want that on my original instance, the query was true, but doctoring this instance to do copies and disconnect the blue, green, red chain makes the query false. And specifically, I want this to make the query false. So this is an interesting instance and pattern for my query. So if I find an instance and a pattern like this for my query, it means I have isolated the behavior of the query. I have seen two very similar instances on which one satisfies the query, the other one does not satisfy the query. I have basically managed to identify what something that my query cares about. So what is this complicated instance here that must violate the query? It's in fact the coding of this RST instance. And the original instance I can be equivalently seen as the coding of that bipartite graph. So to corner my query and see what makes it hard, I want to find an instance in which I want to find an instance that satisfies the query, but that contains three facts such that when I disconnect them in this very specific way of creating two copies of that guy doing 2 copies of the green fact like this and connecting the blue fact to the first copy and the red fact to the second copy, and all other creating copies of all other facts, then this makes the query false. Note that this has a more homomorphism into this. So it couldn't be the case that this one is false and this one is true, for instance. But basically, when I have an instance satisfying the query and I modify it in some fashion that has a homomorphism to here, then I can maybe make the query false. And this is what I want to happen to be able to show hardness. So imagine I have found an instance in a pattern that has this property that doing this disconnection makes the query false. Then, there's a question of whether we can find a pattern like this, which I guess I won't have the time to go into. And the question of, if I find a pattern like this, have I managed to show hardness? How do I use a pattern like this to show hardness? And I will present this because it makes you understand why I needed all of the stuff about bipartite instances before. And finding so let's assume we have found such a pattern. So if we have a query that has a pattern like this, so there is an instance satisfying the query, and modifying the instance in that way does not satisfy the query, then I can just look at bipartite instances that do back and forth paths of increasing length. So consider this sequence of bipartite RST instances, R to T. So this R to T, 1 back and forth, 2 back and forths, and so on. And consider all of the codings that correspond to this. So one coding, this is the coding of one path. This is the original instance, actually. This is the coding of 2 paths. It's very similar to what breaks the query, except that I have this edge here, which is different from this edge here, okay? And I can do the same way, in the same way I can do the coding of a path of length 2 and so on. Basically, I'm trying to I'm getting a sequence of instances between these two to try and pinpoint more precisely what the query cares about between these 2 instances. And it is the case that this has a homomorphism to this, because I can just collapse together all of the B's. And this one will have a homomorphism to that one, and so on. So there are 2 possibilities. Either all of them, either all of these back and forth, all of these can satisfy the query indefinitely. This means that the query wants that there is a path between the blue and the red going back and forth an arbitrary number of times, but that cannot be disconnected, because if it's disconnected, the query says no. The other possibility is that the query eventually stops saying yes, and there is a threshold, a given length, where the query says no. So the query then cares about the fact that blue and red are connected by a green path going back and forth some number of times, but a bounded number of times. After that, the path is too long and the query is saying no. And you see, I mean, I won't show it formally, but intuitively you see that these 2 cases correspond to, if you think about what this means in terms of the bipartite instances. So in one case, we know that the codings of all of these satisfy the query, but the coding of that, we know that this did not satisfy the query. So in that case, the query is actually equivalent to reachability. It's basically asking whether there is a path between red and T of an arbitrary length. And if the query has a threshold and says, I want the path of length 2, but not of length 3, the query is basically saying, this is basically the query that tests whether there is a path between R and T of a specific length. And these are the queries on RST instances, of which we showed that they were intractable. So you see that having this critical pattern in an instance means that I have the coding of this makes the query true, the coding of this makes the query false, and given that I have this homomorphic sequence connecting them, the query, I can reduce from the hard queries on these instances to my actual query on the instances, like on the codings. Okay. So if I have this critical pattern, so if I have this satisfying the query and this breaking the query, then the query is hard. I don't have much time to tell you how we find such a hard pattern. It's slightly complicated. In fact, what we do is we take a large instance and we start messing around with it in this more crude process of taking one edge and disconnecting it by two edges, but not creating any incident facts on the C prime and B prime. So we're not connecting additional things to them. So we're taking a large instance, we are opening up switches, so disconnecting facts like this in an arbitrary way. And we find a place at which one crude disconnection like this breaks the query. And there has to be one, because otherwise the large instances always simplify to something which is hierarchical, like a union of stars if there's nothing left to disconnect. And once we have such a critical switch, such a critical disconnection, by using the right minimality condition, we can guarantee that the most subtle disconnection process done here actually also breaks the query, because if the query is true here, we can do other kinds of disconnections using minimality. This is extremely vague, but it's all I have the time to explain. And this is all that there is. Okay, so it's time to conclude, and it looks like I had planned for slightly too much material. So in conclusion, I've only talked to you, I only wanted to talk to you about the complexity of probabilistic query evaluation, and I've only talked about that. And even then there were too many things to say. So basically what I consider to be the three important cases, at least in the structure of this talk, is self-join-free CQs, which are well understood, I mean, sufficiently well that I could try to explain everything to you, that the hierarchical ones are tractable. And we also have circuit representations of their provenance, which is a modular way to explain the tractability of probabilistic query evaluation. And the non-hierarchical ones are intractable because of these reductions from counting independent sets or whatever. And this works even for probabilities of 1/2 everywhere, like this unweighted uniform reachability. UCQs, I skipped them, so it's understood in the sense that there is a known dichotomy result, so the tractable ones can be solved with an algorithm, and whenever the algorithm fails, the query is hard. But the proofs are very complicated, and they don't cover, so the tractability is not explained in terms of circuits, and it's open whether it can. The uniform reachability, the uniform reliability setting of probabilities of 1/2 everywhere is still open, although like last year there was progress on that front from Koenig and Suchi. And for this larger class of homomorphism closed queries that we introduced, or well, it was known before, but that we studied in that ICDT 20 article, everything is intractable except for UCQs, and there it's not perfectly understood yet, but I'm trying to understand it. There are many other topics about probabilistic query evaluation that I had given up on covering in this talk. So adding negations to queries, adding inequalities to queries, understanding circuits in terms of different tractable formalism for which there are other results. Symmetric model counting, which is a related topic, and there's been results at last year's pods about probabilistic instances with infinite domains, or probabilistic instances where you can do efficient updates, which we talked about before. And of course, there's the question of practical implementation, and for this, I think the main effort currently is by my former PhD advisor, Pierre Senelard, called ProbSQL. So if you ever want to use this in practice, there is a PostgreSQL module called ProbSQL, which allows you to manage provenance circuits and do probabilistic evaluation on top of them using existing model counters. And yeah, so in terms of open problems, there are all of the ones that I mentioned earlier. And I think big questions are, can we do approximate evaluation of approximate probabilistic query evaluation? So it's known in some cases that yes, but there are no very complicated results about that, let's say. And all of these techniques reusable in other contexts. So Wojtek mentioned a hope that they could be useful for something else. I hope that this work can be useful for other things at the specific problem of probabilistic query evaluation. And yeah, more broadly, can we do reasoning? So we've talked about probabilistic constraints and inference for them. Can we reason with like probabilistic rules? This is what we intended to do during my PhD at the very beginning 10 years ago. And then we realized that there were simpler things that were not properly understood yet. Maybe, so I've been hoping in 10 years that we managed to get a reasonable formalism and understanding of this kind of problems, but it's still pretty much open. Okay, so it's time to conclude. Thanks everyone for your attention.
Thanks a lot, Antoine. So yeah, maybe we have some questions. So I have one question, since we are not very many and a lot of us are from Warsaw. So I wrote you in this feedback form but I will tell it loudly. I think more of us is interested in that. So in Warsaw, we recently thought about the following problem, which there is some resemblance. So the problem seems maybe not related, but so typical problem in automata theory is you are given some two systems, you ask, are they language equivalent? But instead of language equivalent, let's say for finite automata, you know how to do it. For, I don't know, automata with one counter, it's undecidable, let's say, even if you accept by state. And for some other, for context-free grammars, it's undecidable. But if you now change your notion of equivalence and ask, okay, two systems are equivalent if for each word, the number of runs in the first system is equal to the number of runs in the second system. So this is more subtle, but there is a hope that maybe it's more decidable. And we try to look at these things, and it's hard to understand the structure. And here you kind of do similar things. So instead of looking, is my query satisfied or not, you try to give a number. So you are considering probabilities, but if you fix probabilities always to 1/2, it's kind of you are counting. Yes.
Yes.
And I wonder whether there were some works, for example, like given two queries, is it true that for each database of a shape, you know, each event has 1/2 of probability? These two queries have the same probability, or some other kind of similar equivalence between queries.
Yeah. But so one thing I can say about that, which is different, is that this would be a question about queries, right? There would be no database, and so you would be interested in the complexity in terms of the queries of solving the problem. But the query complexity the complexity of all of that stuff in terms of the query is hasn't been studied much, and in fact poorly understood. I mean, I think it's explicitly stated that for the UCQ algorithm, it's doing complicated things on the query, and so complicated things that they didn't even give an upper bound. Well, I think that there's probably a crude upper bound, but the precise complexity in terms of the query is not known. And so for that reason, the complexity in terms of the queries of these notions of equivalence, I don't think it's been studied much in our context.
No, decidability would be good in our context. So it's not even clear for me whether it's decidable.
Yeah, it's true. So then the other thing I was thinking about that might relate a bit is one question you could ask is, okay, probabilistic query evaluation for that query is intractable, but is it tractable given two databases to know if they have the query has the same probability on both of them?
Okay.
That's another way of posing the problem in a data complexity perspective. And I guess this would be in your setting, it would be something like, can you efficiently test? This would be if I have some formalism where counting the runs is intractable, can I, given two structures, like two words or whatever, decide if there's the same number of accepting runs on the two of them? Is this simpler than, and I don't know if there's,
but
I have this, yes, sorry, go ahead.
So yeah, I mean, so it seems for me that maybe the more natural problem would be, is it true that for each query they are equivalent? But this probably never happens unless they are equal.
Well, it could with, I mean, if they're homomorphically equivalent, for instance, I mean, and the probabilities are the same. I mean, I could definitely give you dumb examples of, you see like this with probability 1 and this, these two things are equivalent for all CQs and they don't even have probabilities. So certain instances.
Here, okay.
But of course, if I add probabilities, I can start doing things like, well, I don't know what the probability for this would have to be. I mean, there are definitely probabilities P and Q here, so that the two are equivalent.
Mm-hmm.
I don't know exactly how you do that, but whatever solution, probably you can take the two to be equal, and then whatever solution to this gives you a P that works.
Think about such line of research direction.
So I don't know of anything related to that. I have this vague memory that there are some counting problems where people have like the problem of knowing whether two things have the same count could be. I don't know if there's something in complexity that resembles this.
So this is, I think, the like conjunctive queries with the back semantics, right?
There's that, yeah.
Actually, that was my question. Because for that, as far as I know, like the containment problem is a big open problem, and the equivalence is, I think, decidable. It's like graph homomorphism, or I don't remember exactly, but something like that. So, but I'm not sure if what I was saying now is true, but so there the containment problem is undecidable, is open, and I think there was this thing that if you somehow fix the database, I mean, if you just fix it, then it's of course decidable. If you somehow, I don't remember what I mean by this, the problem becomes undecidable.
If what?
That's why it's not somehow, it's not obvious to me. Is it obvious that here like query containment is a much harder problem?
So from what we discussed with Wojtek before, I think query containment wouldn't be more defined. I have the I'm suspecting that it might be in the probabilistic case, it might end up being the same as in the deterministic case.
Yeah, so if you allow for probabilities being 100%, this probably the same. But if you disallow it, maybe your trick works. But
yeah, I tell you that maybe you can just emulate probabilities close to 100% by fact duplication. So. I know. Okay. No. One reasonable thing would be: is there an affine relationship between the two probabilities, like something like can the probability of, and you could say, I mean, saying P, Q, and Q prime are almost equivalent could be something like some constant. Sorry, minus. You see, so something like that, right? You could say. And then like the probability of Q wouldn't be the same as Q prime, but saying like it's within some multiplicative ratio of that of Q prime. And like if this holds for both queries, you could say they are equivalent, like approximately equivalent, something like that. And then maybe something interesting would happen. Well, no, wait a second. I guess not really. No, I guess this isn't so interesting because in the deterministic case, the probability is either 0 or 1, and so if there's a counterexample, it's also a counterexample to this approximate thing.
I'm not sure.
So to continue iterating on your question, Wojtek, and I think that the techniques I've presented, some of them are very specific to this database-ish stuff. The interpolation method, however, is I think more generic, but it's still a way to do a reduction. It's not. It doesn't seem to be a way to get you this undecidability or something.
Okay, thanks a lot. Do we have some other questions? Okay, so thanks for an in-depth tutorial. We will put this on YouTube soon. So I guess more people will see it as well. Okay.
Thanks again for the invitation.
Thanks for the preparation.
Sure.
Okay, thanks. Bye.
See you guys.